to us on constraints on the formation age and evidence for thermal demagnetization of the Moon's Reiner gamma magnetic anomaly. Take it away.
Thank you for that, and thank you to Ian for the lovely intro talk on swirls. So I will be focusing also on Reiner gamma, but more on the tail rather than on the main body. So this is the same image that Ian showed with contours of all the magnetic anomalies on the Moon. And currently, the Moon does not have a global field, and we would like to use the current day crustal magnetic anomalies to get some insight into what the lunar dynamo once was. Because we do not understand any of these magnetic anomalies, a good way to approach them is with the special tool of swirls, which are circled here. And it is interesting to note that all swirls have an associated magnetic anomaly, but not all magnetic anomalies have swirls. So the things that we do know about them is that they all have magnetic anomalies. The surfaces are optically immature. Ian mentioned the shielding from the solar wind ions. And they have none of their own topography. It's just this pattern that is draped over pre-existing topography. And what we don't know is the source body that is causing the magnetic field. And it could be volcanic intrusions or impact ejecta. And depending on what the source is of this body, it can place different constraints on the lunar dynamo. So by working towards understanding where the swirls came from, we can get a better picture of the dynamo. So I am going to split up my analysis into two different types, the first being gravity. The tail of Reiner gamma goes over a particular magnetic anomaly, Bouguer anomaly that I will show you in the next slide. And by figuring out how that formed, we can figure out how the swirl is related to that. And next I will move on to some thermal analysis, because the tail of Reiner gamma goes up to a big volcanic complex, and look at some demagnetization models to place further constraints on swirl formation and thus the lunar dynamo. Okay, so for the gravity analysis first, this map has Bouguer gravity, and the swirl is overlain on top of it. You can see that the tail crosses over this large negative Bouguer anomaly. And this was identified in a paper by Alexander Evans in 2016. Is that one right there, as a quasi-circular mass anomaly, which they argued are most of them buried craters. So it's interesting to note that the anomaly that the tail crosses is negative instead of positive. Typically, craters that have a positive Bouguer anomaly, that's indicative of some upwelling mantle underneath. But in the case of a negative anomaly, you know that there is some less dense material filling this crater. So it could either be ejecta from another impact filling a pre-existing crater, or uplift in the formation of the crater itself. So in the first case, you start with an empty crater that you cannot see at all here. So you'll have to trust me when I say that there is a mound of material there. And imagine that there is the light gray box filled underneath, and the part that is causing the negative anomaly is this bit right there. And then in the case of the uplift from the crater formation, you start with some basalt eruption on top of it, which then uplifts through that, and you end up with the same sort of cross-section as in the first case. But an interesting thing to note about these is that the diameter of the part that is causing the gravitational anomaly is not the same as the part that is the actual diameter of the crater. So to understand how the swirl source body is related to the crater itself, we need to figure out what the actual crater diameter is given the radius of the gravitational anomaly. So here's that same map again. The solid circle shows the size of the anomaly that they identified in the Evans 2016 paper. And we don't know exactly where the crater rim is outside of that. We have a general idea of like what proportion it should be at, but we don't know exactly where it is. And just for comparison with a positive anomaly, here's the topographic rim of the crater, and you can see that it is outside the gravitational anomaly size. So what we can do is we can assume that the part that is causing the gravitational anomaly is the floor of the crater. And in that same paper, they have a relationship between the diameter of the floor and the diameter of the rim. So by using that equation, we can get the diameter of the rim of the crater to be 175 kilometers, which is this dark outside circle. And now we would like to see if that makes sense or not. It's all well and good that we have an answer, but we need to see if it works. And we would like to check on a crater that we can actually see its rim and it has a negative anomaly, but those don't exist because when you make the negative anomaly, everything ends up buried. So you cannot see the actual topographic rim. So the next best thing to do is find a crater of a similar size to see the relationship between the floor diameter and the rim diameter. So we chose Petavius, which is on the near side, right here, and it is 184 as compared to the buried ones calculated 175. And as you can see, they have a similar ratio between the floor and the rim. So to conclude this section, Reiner Gamma, the tail of Reiner Gamma crosses this purported buried crater with a diameter of approximately 175 kilometers. And by determining the age of this crater, we can start to get at the age of Reiner Gamma and thus put constraints on the lunar dynamo. And to tie this back to what Ian was saying, if this is a crater, it is important to note that the relationship there with the main body of the swirl is outside the rim of the crater. So if there is a disk, it's not being interrupted by the rim of the crater. So moving on to the second part now, not to confuse you with my color maps, this is showing topography now. These are the Mariusz Hills, which is a very densely erupted volcanic complex on the moon. And again, here is Reiner Gamma shown coming right up to the Mariusz Hills. And if the swirl was formed before the Mariusz Hills formed, when they emplaced all that heat into the crust, thermal demagnetization could have occurred of the source bodies. And if the global field at that time was either weak or non-existent, the demagnetized source bodies would not subsequently remagnetize. So by putting a date on when the Mariusz Hills were formed, we can further constrain the age of the lunar dynamo. So I'm zooming in now to the yellow subset box. And to kind of set everything out for you here, this shows the path of the swirl going right up to the edge of a volcanic plateau and weaving through some volcanoes here. And the most important part to notice about this is that the brightest parts of the swirl are never imprinted on top of local maxima in topography, which are the volcanoes where the most heat would be. So to zoom in a little bit further to show you the relationship between the swirl and a specific volcano, this is the path of the swirl wrapping right around the flank of the volcano, and you can see that it does get slightly less bright right next to it, showing potential partial demagnetization. So what we would like to do next is make a simple thermal model of this. And the goals of this model are to determine if demagnetization is actually happening in this instance and to learn more about the Mariusz Hills region themselves. So we have inputs and outputs to the models. If you would like more details on this model, you can come talk to me afterwards and I can tell you all about it. The inputs to this are things that we can measure when we look at the map. So the things that we can measure are the size of the volcanoes and also how far out the swirl is demagnetized, and we're calling those B and Y. And the output of the model is the thing that we calculate, which is the fill fraction of the volcanoes or volcanic regions, which is what fraction of the volume is filled with magma at any given time. So when we use this model, we get fill fractions between 14 and 50%. We're showing that this model is physically feasible and that thermal demagnetization could be occurring. So the next thing to do after showing that it is occurring, we would like to figure out the age of the Mariusz Hills, because when that injected all the heat into the area and demagnetized the source body and did not subsequently remagnetize, we know that it was either a weak field time or a no field time. So this is from an LPSC abstract where they were dating areas in the Mariusz Hills using crater counting. This first image shows shield volcanoes, and here is the tail of the swirl coming right up into the Mariusz Hills. And as you can see, there's a pretty wide range of ages right next to the swirl. There's about 3.3 all the way up to 1.4 billion years. So by looking at this region a little more closely and figuring out like specific ages of things right next to the swirl, we can put stronger constraints on it. And the second image here shows the not volcanoes, but the surrounding basalts next to them. Their ages are slightly older. And both of these cases we can use to more closely constrain the age of the Mariusz Hills. So to sum up this section, Reiner gamma is right near the Mariusz Hills, and our first order calculations indicate that thermal demagnetization is happening there. And by determining the age of the Mariusz Hills, we can put an age on when demagnetization and no subsequent remagnetization was happening. And with that, I can take questions.
Hi, this was really cool. I'm sorry if I missed it, if you said it. What's the minimum temperature at which the demagnetization will occur?
I think what we were using in our model was around 1,000 Kelvin. Around there, yeah. If you want, I can look up the specific temperature that we use, but I can't think of it off the top of my head.
Okay. No,
it's also a time temperature thing, so it's not just if you sit at 300 degrees for a billion years, the whole thing could be demagnetized.
Okay.
So if it's 600 degrees for 10 minutes, then it's a time temperature.
Okay.
Yeah.
Thank you.
I think you said this, and I was taking notes, and so I just want to make sure I understand. So we have this wide variety of ages for the Mariusz Hills from crater counts, but the older ages are presumably still happening when there may be a lunar dynamo taking place. And so in some sense, you can rule out the older ages in favor of the younger ages. Is that correct? Does that give you an extra constraint? Because if you demagnetize it, then if you still have a magnetic field in the moon from the dynamo, then it's gonna pick it back up again.
Yes, so you're saying that the older, go back to it.
I'm saying, like imagine that the Mariusz Hills were 3.7 billion years old.
Mm-hmm.
I think that's still when the dynamo is still pretty active on the moon.
Yes.
And so you wouldn't demagnetize things because there's still a dynamo. When the hot surface goes below the Curie point, it'll pick up whatever dynamo signal is coming at that point from the magnetic field, right? So I think you can rule out some of those older ages.
Right. So you're saying that if this entire region was cooling, when it was a dynamo field, then why isn't the whole surface magnetized?
Or I guess what I'm saying is that essentially you can look at sort of the Ben Weiss curves and the other people's curves as to when the dynamo goes away, and that's sort of the upper limit because these places are demagnetized for the age of the Mariusz Hills.
Right, that is true.
Yeah. So
yes, that could be used as.
So actually, you're helping us get at the age of the Mariusz Hills too with this, which is interesting. So,
yes.
Yeah.
Yes.
Yeah, they both help each other. So
yes.
Okay, great. Thanks, Megan.
Thank you.
Great talk.